Picture the darkness that exists beyond the last planet. Not the comfortable darkness between stars where light still travels freely in every direction, but a specific, geographically definable darkness. A place where the sun has shrunk to the size of a bright star in your sky. A place where temperatures hover near absolute zero. A place where a single orbit around that distant pale fire might take 24,000 years to complete. This is the outer solar system, and it is not empty. It has never been empty. We simply had not been looking in the right way, with the right instruments, at the right time. What lurks out there? That is the question that has consumed careers, redirected billion-dollar satellites, and woken astronomers at 3 a.m. with a specific cold feeling in their chest. Not dread, not quite, but its more productive cousin. The pressing sensation that the thing you are looking for has always been there, right behind the curtain of our technological limitation, and that the curtain is finally beginning to tear, because in the last decade, something extraordinary has been happening at the edge of our solar system. Not one thing, not a single discovery handed to us neatly by the cosmos. Several things. A cascade of discoveries, each one capable of standing alone as the most consequential solar system finding in a generation, but arriving so closely together that collectively they force us to ask a question that the standard model of planetary science had considered closed. Do we actually know what lives in the outer darkness? In 2025, a possible new dwarf planet was pulled out of archival telescope data. A world roughly 700 kilometers wide, hurtling through a 24,256-year orbit that swings it from the inner Kuiper belt to the doorstep of the Oort cloud. That same year, researchers in Taiwan cross-referenced 2 infrared satellite surveys taken 23 years apart and found what might be the first thermal fingerprint of a world 5 to 17 times the mass of Earth, sitting in the dark some 500 to 700 astronomical units from the Sun. And all of it arrived against a backdrop of Voyager 1's recent near-death experience, a garbled transmission from 24 billion kilometers away that forced a team of engineers to perform open-heart surgery on a half-century-old computer from across the solar system itself. We are not discovering the edge of our solar system. We are discovering that we never understood it in the first place. That story begins, as the best stories usually do, with something unexpected in an old photograph. There is a particular kind of scientific confidence that comes not from certainty, but from the absence of evidence to the contrary. For most of the 20th century, the solar system had a comfortable shape in the minds of the people who studied it. There was the sun, there were the planets, 4 rocky ones close in, and 4 giant ones further out. There was a thin band of rocky debris called the asteroid belt between Mars and Jupiter, and beyond the outermost giant, Neptune, there was, for the most part, nothing. A vast, emptying silence that eventually became the void between stars. The idea that there might be structure, populations, perhaps even undiscovered worlds lurking beyond Neptune, had no real observational foundation until 1992, when astronomers David Jewett and Jane Liu discovered the first confirmed trans-Neptunian object, a body designated 1992 QB1. A lumpen piece of ice and rock no more than about 200 kilometers across, sitting serenely some 44 astronomical units from the Sun. That is 44 times the Earth-Sun distance, or roughly 6.6 billion kilometers. Far, very far, but not, as it turned out, anywhere close to the actual boundary of things. Their discovery opened the door to what we now call the Kuiper belt, a donut-shaped ring of icy bodies extending from about 30 to 50 astronomical units out from the Sun, and by current estimates containing hundreds of thousands of objects wider than 100 kilometers, with a total mass somewhere between 1 and 2% of Earth's. Pluto, reclassified in 2006 as a dwarf planet, rather than a full-sized member of the planetary family, is the Kuiper belt's most prominent resident, orbiting between roughly 30 and 49 astronomical units from the Sun. It has company in the form of Eris, Makemake, Haumea, and dozens of other designated dwarf planets. plus a vast, uncounted population of smaller bodies that surveys have only begun to characterize. The Kuiper Belt gave the solar system a new and richer ending, or so it seemed. Here was the destination beyond Neptune, a reservoir of primordial material, ancient debris from the formation of the planet's 6 billion years ago, preserved in the deep freeze of the outer solar system like flies caught in amber. The Kuiper Belt fit neatly into theories of how the solar system formed. It explained where short-period comets came from. It gave Neptune a coherent gravitational role as the shepherd of this outer population. Pluto had a home, and then Sedna arrived, and the whole map had to be redrawn November 14, 2003. Astronomer Mike Brown, a Caltech planetary scientist, who would later describe his own career as a decades-long project to comprehend the solar system's true complexity, was running a survey program at the Samuel Oschin Telescope at Palomar Observatory in the mountains east of San Diego. His team, also including Chad Trujillo of the Gemini Observatory and David Rabinowitz of Yale University, was systematically photographing large areas of sky and then comparing the images to find moving objects. It is a technique that dates to the photographic plates of the early 20th century, but by 2003 it had been supercharged by digital detectors capable of imaging areas of sky hundreds of times wider than earlier equipment, and computers fast enough to check for movement across thousands of candidate positions automatically. The object they found that November night should not have been where it was. Every body the team had seen previously in the outer solar system fit, however imperfectly, within the broad strokes of what planetary dynamicists had predicted. This did not. It was later given the name Sedna, after the Inuit sea goddess said to dwell in the cold depths of the Arctic Ocean, a name that captured, with unusual precision, the character of the world it was attached to. Sedna's orbit is, even now, one of the most extreme known in the entire solar system. At its closest approach to the Sun, its perihelion, it reaches approximately 76 astronomical units. That is already nearly 2.5 times further than Neptune, but Sedna swings out to an aphelion of roughly 930 astronomical units, nearly 1,000 times the Earth-Sun distance, before looping back over a period estimated at around 11,400 years. The orbit is an enormous thin ellipse, a comet-like trajectory of staggering proportions executed by an object several hundred kilometers across, and so red in color that it stands out from the surrounding objects like a bloodstain on fresh snow. The problem Sedna immediately created for solar system science was not just one of scale, though the scale alone was extraordinary. The problem was dynamical. The Kuiper Belt's bodies had orbits that could be explained by the gravitational influence of Neptune. Neptune is, in the outer solar system, the dominant gravitational architect. Its gravity sculpts the distribution of Kuiper Belt objects in ways that are well understood and well modelled. Sedna's perihelion distance of 76 astronomical units puts it far beyond Neptune's sphere of meaningful influence. Neptune's gravitational reach, for practical orbital purposes, extends to perhaps 50 or 60 astronomical units at the outer extreme. Sedna was sitting far outside that zone, in a region where nothing in the standard model gave it any right to be. So how did it get there? 3 broad categories of explanation were proposed in the years after the 2004 announcement of the discovery. The first, and for many dynamicists, the most appealing, invoked the Sun's stellar neighbourhood during the earliest period of solar system formation. For the first few 100 million years of its existence, the Sun was almost certainly not the isolated middle-aged star it is today. It was embedded in a stellar nursery, a dense cluster of young stars forming simultaneously from the same molecular cloud. In that dense environment, passing stars would have been far more common than they are today, close encounters on timescales of millions rather than billions of years. If a star passed within a few thousand astronomical units of the young Sun, its gravitational tug could have yanked bodies from the proto-Kuiper Belt into highly elongated orbits precisely like Sedna's. That star then departed, taking with it the evidence of the encounter, leaving only the trail of distorted orbits as testimony. The second explanation, slightly more exotic, suggested that the Sun may have captured Sedna from another star's planetary system during one of those ancient close encounters. Bodies orbiting another star, perturbed by the near collision, could have been exchanged between stellar nurseries. Sedna, on this account, is not native to our solar system at all. It arrived as a refugee from another star's empire billions of years ago. The third explanation, and the one whose implications cascaded forward into everything that has followed, suggested something far closer to home, that a planet, a large, unseen, massive planet, was still out there, orbiting far beyond Neptune, and that its gravitational influence was responsible for sculpting the orbits of Sedna and anything else that lived in that remote region. This was the first serious modern incarnation of what would eventually become the PlanetNine hypothesis. It sat, largely unstated, in the back of many astronomers' minds for the decade that followed Sedna's discovery. A question without enough data to answer, a hypothesis without enough evidence to defend. The data began accumulating slowly. Over the years between 2004 and 2014, surveys continued to map the outer solar system, finding hundreds of new Kuiper Belt objects and gradually extending the observational database of bodies beyond Neptune. Most of what they found was consistent with what the models predicted, but not everything. By 2014, a handful of bodies had been identified with orbital properties that echoed Sedna's, sitting in regions of the solar system where they had no business being unless something was pushing them. Then, in March of that year, Scott Shepard of the Carnegie Institution for Science and Chad Trujillo, who had been part of the original Sedna discovery team, announced the discovery of 2012 VP-113, a body nicknamed Biden after the then US Vice President, because its designation started with the letters VP. Biden's orbit was eerily similar to Sedna's, with a perihelion distance of about 80 astronomical units and an aphelion extending to approximately 452 astronomical units. The Sednoid population, bodies like Sedna living in the inner Oort cloud region, detached from Neptune's influence, suddenly had two members. Trujillo and Shepard went further. They pointed out something in the data that would, in 2 years, become the central exhibit in one of the most contentious debates in modern planetary science. Several of the most distant known Kuiper Belt objects and sednoids appeared to share similar orbital orientations. Their perihelia were clustered in the same region of sky, their orbital planes were inclined similarly, and the arrangements were consistent across multiple independent objects. This was not what you would expect from a random distribution. In a solar system with no undiscovered large planet, the distant objects should be distributed randomly around the orbit of the Sun, pushed into every possible orientation by the combined impartial nudges of Neptune, Jupiter, Saturn, Uranus, and the galactic tide. They were not randomly distributed. They were gathered together as if something with mass, something with gravity, was herding them. This was the setup for everything that followed. It was the data point that Konstantin Batygin, a young and exceptionally talented planetary theorist at Caltech, could not stop thinking about. It was the reason the phone rang one day in January 2016, and the headline appeared in newspapers and websites around the world. There might be a ninth planet, and it might be enormous, and it had been lurking in the darkness for billions of years without us ever seeing it. The subsequent decade, the period we are now living through, has been the most turbulent, productive, frankly nerve-wracking chapter in the history of outer solar system science. The map we thought we had has been crumpled, smoothed out, redrawn, crumpled again. What we have discovered in its place is not a neater map. It is a territory we are only beginning to understand, rich, bewildering, and far more consequential than anyone who drew the old map ever imagined. In January 2016, Konstantin Batygin and Mike Brown published a paper in the Astronomical Journal with a title that managed to be simultaneously technical and electrifying, evidence for a distant giant planet in the solar system. In the way that all revolutionary papers must, it began with data. The data in question involved 6 trans-Neptunian objects with semi-major axes greater than 250 astronomical units. Bodies sitting so far from the Sun that they spend most of their orbits in a region of space so remote it had been effectively invisible to prior survey programs. What Batygin and Brown showed was that the arguments of perihelion of these 6 objects, the orbital elements that describe the direction in which each body's elongated orbit points, essentially the compass bearing of each orbit's closest approach to the Sun, were clustered within a remarkably narrow range, not just somewhat similar, aligned in a way that could not plausibly be attributed to chance. The probability they calculated that this alignment would occur randomly, without some gravitational shepherd organising the orbits, was approximately 0.007%. That is a 1 in 14,000 chance. In most areas of science, finding a result that has a 1 in 14,000 probability of being due to chance would constitute extraordinary evidence that something real and physical is causing the observation. To be clear about what clustering means here, because it is worth inhabiting the physics for a moment. Imagine throwing 6 darts at a dartboard the size of a wall. If you throw them randomly, they will scatter all across the wall. Finding all 6 darts within a 30-degree wedge of that wall would be, to put it gently, suspicious. The clustering of these trans-Neptunian orbits was the astronomical equivalent. Not just their perihelia pointing in the same direction, but the planes of their orbits all tilting in the same sense, all inclined relative to the plane of the solar system at angles that were consistent with perturbation by a single massive, distant object. Batygin and Brown ran computer simulations, and the picture that emerged was arresting. They found that a planet with a mass greater than 10 times that of Earth, roughly the size of Neptune, in other words, orbiting in a highly elongated trajectory with a semi-major axis of approximately 700 astronomical units and an orbital period of perhaps 10,000 to 20,000 years, placed anti-aligned relative to the clustered bodies it was herding, could reproduce all of the orbital features they were observing. The planet would sit, on average, at a distance from the Sun that light would take roughly 97 hours to cross, compared to the 8 minutes it takes to reach Earth from the Sun. At its farthest point from the Sun, this hypothetical world would be more than 1,000 astronomical units away. At perihelion, it would still be further from the Sun than any known planet in the solar system by a factor of more than 10. I should tell you how I feel about this, because it is relevant to how I think we should approach the rest of this story. I find the PlanetNine hypothesis one of the most audacious and genuinely thrilling propositions in modern science. Not because I am certain it is correct. I am not, and neither are its proponents, but because it represents science at its best. It is a case of reasoning from sparse, ambiguous, difficult to collect data towards a hypothesis that is bold, specific, and in principle falsifiable. Batygin and Brown were not saying there might be something vaguely large out there. They were saying there is a planet. It is roughly Neptune-sized. Here is the approximate region of sky you should look in, and here are the orbital properties it must have if our data are right. That is a testable prediction. That is real science, but the scientific community, quite rightly, did not simply accept it. The decade that followed the 2016 paper was characterized by a vigorous debate about whether the clustering was real, whether the statistical analysis was sound, and whether alternative explanations could account for the observations without invoking an undiscovered planet. The first and most important line of criticism concerned observational bias. When you survey the sky for distant trans-Neptunian objects, you do not survey it uniformly. Survey telescopes have fields of view, observing schedules, and regions of sky they preferentially cover. Most dedicated survey programs concentrate near the ecliptic plane, the great circle on the sky traced by the Sun's apparent path through the year. Because most solar system objects have low orbital inclinations and spend most of their time near the ecliptic. If your survey disproportionately covers one region of sky rather than another, You will find more objects in that region, not because more objects are there, but because that is where you were looking. The objects you find will cluster artificially, mimicking what a real physical clustering would look like. This is the observational bias problem, and it is not a hypothetical concern. It is an absolutely real and well-documented feature of astronomical surveys. A 2017 analysis by Brown himself attempted to account for this bias and concluded that even after correcting for survey geometry, the clustering remained statistically significant, though with somewhat reduced confidence. But subsequent analyses using different survey samples reached different conclusions. A 2021 study using 14 extreme trans-Neptunian objects from the Dark Energy Survey, the Outer Solar System Origins Survey, and the Shepard-Trujillo Survey found joint probabilities for uniform distribution ranging from 17 to 94%, meaning the data, properly corrected for bias, could plausibly be consistent with a random distribution. The same study concluded that it could not explicitly rule out PlanetNine, but the statistical foundation for inferring its existence appeared shakier than the 2016 paper had suggested. So by the early 2020s, the situation was genuinely unclear, not in the way that scientific situations are sometimes falsely described as unclear, where one side has overwhelming evidence and the other is clutching at straws, but in the authentic sense. The clustering signal, which had motivated the entire hypothesis, was real in some analyses and vanished in others depending on which objects you included, which surveys you corrected for, and which statistical methodology you applied. The hypothesis was alive, but it was wounded. It needed new evidence to either confirm it or kill it cleanly. What it got instead was something far more complicated. In 2024, Batygin, Brown, and collaborators published an updated analysis. This one included a larger sample of objects and applied a more sophisticated treatment of observational bias than any previous study. The result, they argued, was compelling. The PlanetNine inclusive dynamical model was rejected at a 5 sigma confidence level against the PlanetNine free model. 5 sigma is the gold standard of modern physics, the threshold typically required to claim a discovery in particle physics. This was not a detection of the planet itself, but a statistical argument that something in the outer solar system was organizing the orbits of these distant objects in a way that could not be explained without PlanetNine. The paper landed in the community like a brick thrown through a quiet room. The skeptics were not silenced, but neither were the advocates. And then, just as this debate was reaching its most recent and heated iteration, a new object appeared. An object that simultaneously strengthened some aspects of the case for hidden structure at the edge of the solar system and cast a quiet but consequential shadow over the simplest version of the PlanetNine hypothesis. The object's name is 2017 OF201, and its orbit, and computed precisely from 19 separate observations taken across 7 years of archival telescope data, describes one of the most extraordinary trajectories ever traced by a solar system body. Its perihelion sits at 44.9 astronomical units from the Sun, which puts it just outside Neptune's orbit. Its semi-major axis, the average of its closest and furthest approach, which describes the overall size of the orbit, is 838 astronomical units. Its aphelion, the furthest point it reaches in each orbit, is approximately 1,632 astronomical units, and it takes 256 years to complete a single revolution around the Sun. Pause on that number for a moment. 24,256 years. The last time 2017 OF201 passed this close to the Sun, it was November 1930, the same year Pluto was discovered. Coincidentally, though the alignment is astronomical rather than meaningful. The next time it will come back to where it is now, making another close pass as it dips into the inner fringes of the solar system. The year will be approximately 26,256 CE. Whatever civilization exists to witness it, if any does, it will be as different from us as we are from the ancient Sumerians who first scratched astronomical observations onto clay. But here is the thing about 2017 OF201 that matters most for the debate about what lurks at the solar system's edge, its longitude of perihelion, the orbital property that describes which direction in space its closest approach to the Sun points, is 306 degrees, and that number places it squarely outside the cluster, in the distribution of extreme trans-Neptunian objects that has been used to argue for PlanetNine, the other objects in this dynamical family cluster around a perihelion longitude of approximately 60 degrees. 2017 OF201 is an outlier. Its orbit does not fit the gravitational herding pattern that PlanetNine is supposed to produce. And that matters enormously, for reasons we will get to in detail, but first we need to understand just how hard these objects are to find, and what it means that we have found another one at all. The brightness of a solar system body, when observed from Earth, decreases with the fourth power of its distance from the Sun. This is the inverse fourth power law that governs reflected sunlight. Twice as far means 16 times fainter, at 90 astronomical units from the Sun, which is roughly where 2017 OF201 sits at present. An object reflects only 1/6 millionth the light it would reflect if it were at Earth's distance. Finding it in archival telescope data is, to borrow an analogy from the paper's lead author Sihao Cheng of the Institute for Advanced Study in Princeton, rather like finding a coin on the floor of a room by examining the room's shadow from outside the building. The coin is there. Finding it requires not just powerful instruments but extreme ingenuity in how you use them. Cheng and his collaborators, Jiaxuan Li and Eritas Yang of Princeton University, did not build a new telescope to find 2017 F201. They searched archives. Specifically, they dug through the imaging data of the Dark Energy Camera Legacy Survey, a wide-field optical survey whose primary scientific purpose was cosmological rather than solar system-oriented. It was designed to map the large-scale structure of the universe, not to hunt for frozen worlds in our own backyard. But its data covered enormous areas of sky with multiple epochs, and Cheng's team developed an algorithm capable of identifying faint, slowly moving objects in this data that dedicated solar system surveys had missed. What they found was an object that, at the time of its discovery announcement in May 2025, had already been observed in archival images taken between 2011 and 2018. Images that had been sitting on data servers for years, waiting for someone to look at them with the right question in mind. This is, to my mind, one of the most striking features of the current era of solar system science. We are not merely discovering new things with new instruments. We are discovering new things by re-examining old data with new algorithms and new questions. The data existed. The object was photographed multiple times across 7 years of observations. It simply had not been identified as what it was, because no one had yet developed the computational tools to pull it from the noise. The outer solar system is hiding its secrets, not in inaccessible regions of space, but in plain sight, in archives, in data servers, in the terabytes of images generated by survey programs whose primary ambitions lay elsewhere. What else is hiding in those archives? How many objects like 2017 OF201 exist? Objects large enough to qualify as dwarf planets, with orbits stretching from the Kuiper Belt to the inner Oort cloud, that we simply have not found yet. Cheng and his team estimated, based on the probability that their survey would have detected 2017 OF201 given its orbit, that the total population of similar objects could represent approximately 1% of Earth's mass, comparable to the total mass of the entire known Kuiper Belt. A vast, unseen collection of frozen worlds in orbits so extreme that they spend only 0.5% of their orbital period anywhere near the Sun. The outer solar system is not a sparse desert. It is a teeming, barely charted wilderness. And somewhere in that wilderness, something may be doing the herding. To understand why 2017 OF201 creates problems for the simplest version of the PlanetNine hypothesis, and simultaneously why those problems are not fatal to the idea of hidden structure at the outer solar system, you need to understand what a gravitational shepherd actually does to the orbits of the bodies it corrals. Gravity at these distances works on geological timescales. The interaction between a hypothetical planet 9 and the distant trans-Neptunian objects it influences is not a collision, not a brief gravitational encounter, but a sustained, resonant gravitational conversation conducted over millions of years. The planet, wherever it is, however massive it is, exerts a weak but persistent tidal force on the objects in its neighbourhood. Over millions of orbital periods, this tidal force can preferentially preserve certain orbital orientations while destroying others. Objects whose perihelia are aligned against Planet Nine's own perihelion direction, anti-aligned, in the technical language, find their orbits stabilised. They are, in a rough sense, shepherded into the gravitational shadow behind the planet, where they spend the minimum amount of time in the planet's vicinity, and thus receive the minimum destabilising torque. Objects in other orbital orientations get perturbed out of the region entirely, scattered into the inner solar system or flung into interstellar space. What remains is a population that appears artificially clustered, concentrated in the orbital configuration that Planet Nine's gravity preferentially preserves. This is the gravitational herding mechanism. It is elegant, it is mathematically rigorous, and it makes specific, testable predictions. If Planet 9 is responsible for the clustering of extreme trans-Neptunian objects, then the clustered objects should have specific orbital orientations relative to Planet 9's predicted position. An object like 2017 OF201, whose perihelion longitude sits well away from that cluster, should, on the simplest version of the model, be rare or absent. The planet's gravity should have long ago perturbed such an object out of its current orbital configuration. Yet 2017 OF201 is there. It has a precisely determined orbit, confirmed by 19 observations across a 7-year arc. It is not a marginal detection subject to large orbital uncertainty. Its perihelion longitude of 306 degrees is simply and unambiguously inconsistent with the apsidal clustering that the Planet 9 hypothesis seeks to explain. The team that discovered 2017 OF201 were explicit about this in their paper, published in the Astrophysical Journal Letters in 2025. The longitude of perihelion of 2017 OF201 lies well outside the clustering observed in extreme trans-Neptunian objects, which has been proposed as dynamical evidence for a distant, undetected planet. There are several ways to interpret this. The most direct interpretation is that 2017 OF201 challenges the hypothesis, and this is how some commentators responded to the discovery. If the simplest Planet 9 model, a single massive planet in a highly eccentric orbit, producing a coherent clustering of distant Kuiper Belt objects, were correct, you would not expect to find a large, well-determined object in this orbital configuration. Its existence suggests either that the clustering signal is less clean than the hypothesis requires, or that the reality is more complex than a single shepherding planet. But the most direct interpretation is not necessarily the correct one, and the planetary dynamicists who work on this problem are careful not to reduce it to a simple binary. The Cheng et al. Paper does not say Planet 9 cannot exist. What it says is that the existence of 2017 OF201, with its outlier longitude of perihelion, is difficult to accommodate within the simplest dynamical picture. There are more complex versions of the Planet 9 model, involving different mass estimates, different orbital eccentricities, or additional undetected objects, contributing to the dynamical architecture that might naturally produce a mixed population of clustered and unclustered objects. The discovery of 2017 OF201 narrows the parameter space of Planet 9's possible properties. It does not eliminate the hypothesis. Moreover, the orbital dynamics of 2017 OF201 itself are genuinely strange, and the strangeness is not simply a problem for Planet 9 advocates. The orbit of 2017 OF201 has an aphelion of approximately 1,632 astronomical units. At that distance, the galaxy itself begins to matter. The Milky Way exerts a tidal force called the galactic tide that at distances beyond about 1, Zeros in astronomical units becomes large enough to perturb the orbits of solar system objects on timescales shorter than the age of the solar system. The galactic tide is responsible, in whole or in large part, for shaping the Oort cloud, the vast spherical reservoir of comets that surrounds the solar system at distances from roughly 2,000 to perhaps 200,000 astronomical units. 2017 OF-201, with its aphelion dipping into the inner Oort cloud, lives at the boundary between the two dynamical regimes, the region dominated by planetary gravity at its perihelion, and the region dominated by galactic and stellar tides at its aphelion. Objects in this boundary zone have complex, long-term orbital histories that are genuinely difficult to model even with the most sophisticated N-body simulations. This is the problem with building a clean argument from the distribution of extreme trans-Neptunian objects. Each new object discovered at these distances potentially belongs to a different dynamical population with a different orbital history. Some may have been placed in their current orbits by PlanetNine. Some may have been placed there by close stellar encounters during the Sun's early life in its birth cluster. Some may have been sent into elongated orbits by the galactic tide, acting over billions of years. And some, potentially including 2017 OF-201, may have arrived at their current orbital configuration through a combination of all three mechanisms operating on different timescales. Distinguishing between these scenarios from the orbital data alone is extraordinarily difficult. There is also the question of what we are not seeing. The outer solar system survey data available to astronomers in 2025 is enormously better than what was available in 2016, but it is still deeply incomplete. Objects sitting at distances greater than 60 astronomical units are at the practical limit of most optical survey telescopes, unless they are very large or very bright. Objects in high inclination orbits, far from the ecliptic plane, are rarely targeted by surveys that concentrate their observing time near the ecliptic, and objects currently sitting at the far end of their highly elongated orbits, like a hypothetical PlanetNine at aphelion, hundreds or thousands of astronomical units away, could be present in the data and simply below the detection threshold of current instruments. This is the detection problem, and it is the deepest reason why the existence of PlanetNine remains genuinely uncertain nearly a decade after the hypothesis was first published. The absence of a detection is not evidence of absence, it is evidence of our current limitations. A Neptune-sized planet at 1,000 astronomical units, at the predicted perihelion temperature of roughly 47 Kelvin above absolute zero, reflects light so faintly in optical wavelengths that it would be invisible to any ground-based optical survey operating today. Finding it requires either a space-based infrared survey, an extraordinarily deep optical survey covering enormous areas of sky at high galactic latitudes, or extraordinary luck, the Vera C. Rubin Observatory, the newest major ground-based astronomical facility, which began its formal 10-year legacy survey of space and time in 2026, is widely regarded as the instrument most likely to either find PlanetNine or definitively rule it out across large portions of the predicted parameter space. The Rubin Observatory's main mirror is 8.4 meters in diameter. Its camera covers a field of view roughly 50 times wider than a typical research telescope, and its survey will reach limiting magnitudes deep enough to detect a Neptune-sized planet at up to several hundred astronomical units from the Sun. If PlanetNine exists and is currently near perihelion, where it is brightest and slowest moving relative to the background stars, Rubin should find it within the first few years of operation. If Rubin completes its decade-long survey and finds nothing, that will itself be informative, ruling out the simplest versions of the hypothesis over large areas of sky and potentially shifting the scientific consensus away from a planetary explanation for the orbital clustering. But there is a more immediate candidate demanding attention, because in April 2025, before Rubin had begun its full survey, a team of astronomers from Taiwan, Japan, and Australia published a result that the scientific community received with a mixture of genuine excitement and carefully calibrated skepticism. They had found, in the far-infrared data of 2 satellite surveys taken 23 years apart, what appeared to be the thermal signature of a slowly moving object at a distance of 500 to 700 astronomical units from the Sun, a distance consistent with PlanetNine at or near its predicted perihelion position. This was not a visual observation. It was not an image of a planet. It was a pair of source detections in far-infrared catalogues, displaced from each other on the sky by an amount consistent with the orbital motion of a body at several hundred astronomical units distance, and detected at 2 separate epochs 23 years apart, with no other explanation readily available. One detection appeared in data from the Infrared Astronomical Satellite, which conducted its all-sky survey in 1983. The other appeared in data from the Japanese Akari satellite, which conducted its own all-sky infrared survey in 2006 and 2007. The 23-year gap between surveys was the key. A fixed background source, a star, a galaxy, would appear at the same sky position in both surveys. A body moving at the expected orbital velocity of PlanetNine would appear displaced by the expected amount. The single best candidate the team identified showed the expected displacement and was absent from the same sky position in each survey's counterpart observation. Exactly what you would expect from a slow-moving solar system object, rather than a fixed astrophysical source. 13 candidate pairs survived the team's selection criteria from an initial trawl of nearly 1 million sources in the Akari Monthly Unconfirmed Source List. After rigorous image inspection to eliminate artifacts, instrumental noise, and known background sources, 1 strong candidate survived. A pairing of an IRAS detection and an Akari detection separated by 42 to 69.6 arc minutes on the sky, consistent with the heliocentric distance range of 500 to 700 astronomical units and the mass range of 7 to 17 Earth masses. This is not a confirmed detection. The team was explicit about that. IRAS and Akari data alone are insufficient to determine a full Keplerian orbit. The candidate requires follow-up observations with a modern telescope. The paper specifically mentioned the dark energy camera, DCAM, which could potentially detect the object within about 1 hour of exposure if the candidate's position were properly computed from the 2 archival detections. As of mid-2025, those follow-up observations were in progress, with results expected to either confirm the candidate as a slowly moving solar system object or eliminate it as a spurious association. The community's response was measured. Some researchers expressed genuine excitement at the specificity of the candidate. Unlike previous PlanetNine searches, which had produced no candidates at all, this one came with a position on the sky and a brightness consistent with the predicted properties of PlanetNine. Other researchers were careful to note that far-infrared sky surveys are notoriously difficult to work with, dense with artifacts, and prone to the kind of false positives that rigorous follow-up invariably eliminates. The galactic cirrus, extended emission from cold dust in the plane of the Milky Way, is particularly problematic, filling the far-infrared sky with structure that can mimic point sources in ways that are difficult to distinguish from real detections. What is not in question is the significance of the attempt. The far-infrared approach to finding PlanetNine has a theoretical advantage that optical searches do not. At vast distances from the Sun, a cold planet radiates thermally at far-infrared wavelengths, and that thermal radiation decreases with only the inverse square of distance, rather than the inverse fourth power that governs reflected visible light. Far infrared is inherently more sensitive to cold, distant objects than optical light. The 1983 IRAS mission, launched in the same year that Voyager 2 flew past Saturn, and the 2006 Akari mission, launched the same year New Horizons departed for Pluto, were never designed to search for PlanetNine. The hypothesis did not yet exist when their instruments were being designed, but they surveyed the entire sky. Everything above their detection thresholds that was in the sky at the time of their observations was recorded. If PlanetNine was warm enough and close enough to fall above those thresholds, it was in there, somewhere in those archives. The candidate may have been waiting for 40 years. That idea, that the answer to one of the most profound questions in modern solar system science might be sitting in data collected before most of the scientists searching for it were born, is one I find genuinely difficult to put down. While the theoretical debate about PlanetNine consumed the conference rooms and preprint servers of the planetary science community, a different category of discovery was unfolding at the actual physical boundary of the solar system. Not the gravitational boundary defined by the Sun's orbital influence over distant icy bodies, but the electromagnetic boundary defined by the Sun's outflowing plasma, the heliopause. The Sun is not merely a ball of fusing hydrogen. It is also an extraordinarily powerful plasma engine, perpetually exhaling a river of charged particles, electrons, protons, and heavier ions, at speeds between 400 and 800 kilometers per second, in all directions simultaneously. This outflow, called the solar wind, has been blowing continuously for 4.6 billion years. As it expands outward, it pushes against the interstellar medium, the thin plasma and magnetic fields that fill the space between stars, and carves out a bubble of solar-dominated space called the heliosphere. The heliosphere is not a sharp boundary. It is a dynamic, pressure-defined region where the solar wind's outward momentum is matched and then overcome by the pressure of the interstellar medium. At the outer edge of the heliosphere lies the heliopause, the boundary where the solar wind effectively stops, where the Sun's plasma merges into the vast sea of interstellar particles. Beyond the heliopause lies, in the most direct and literal sense, the space between stars. NASA's Voyager 1 spacecraft crossed the heliopause in August 2012. Voyager 2 followed in November 2018. Their crossings were not just milestones in space exploration. They were the first direct physical measurements of the heliosphere's boundary, data from which had been eagerly awaited since both spacecraft were launched in 1977. What they found at the heliopause was not the smooth, gradual transition that the simplest models had predicted. It was a shock. Both spacecraft detected what the research community has come to call a plasma wall, a region of temperatures reaching between 30,000 and 50,000 Kelvin, charged particles trapped and compressed into zones of extraordinary heat by the colliding flows of solar and interstellar plasma. This is not the temperature of the surface of the Sun, which reaches about 5,778 Kelvin. It is 6 to 9 times hotter than the solar surface, found at a distance of more than 120 astronomical units from the Sun, in a region that models had expected to be cold. The source of this heat is a process called magnetic reconnection, the same process that powers solar flares and generates the aurora on Earth. At the heliopause, the magnetic field carried by the solar wind meets the magnetic field of the interstellar medium at an oblique angle. Where magnetic field lines of opposite polarity are pressed together, they can break, reconnect in new configurations, and release stored magnetic energy as kinetic energy and heat. The 2024 paper by Turner and colleagues, using Voyager data to characterize what they described as a thick heliopause boundary layer resulting from active magnetic reconnection, found that the crossing was not a sharp transition but a complex, structured zone of interacting plasmas that extended over a significant range of distances. The heliopause, it turned out, was not a wall in the way a wall is a wall. It was more like the boundary of an ocean, turbulent, complex, with waves and eddies propagating across it in both directions. This is extraordinary for several reasons. The first is practical. Spacecraft designed to operate beyond the heliopause must cope with conditions that are genuinely different from what the models predicted, and characterizing those conditions accurately has real implications for the design of future interstellar probes. The second is fundamental. The detailed structure of the heliopause tells us about the interaction between our local stellar neighborhood and the broader interstellar medium, information that is deeply relevant to questions about cosmic ray fluxes, the bombardment of the early Earth by interstellar particles, and the habitability conditions on planets orbiting other stars. But the Voyager discoveries do not stop at the hot plasma wall. Once both spacecraft crossed into interstellar space, Voyager 1 began returning data about the density of plasma in the local interstellar medium, and what it found was distinctly odd. Astronomer Stella Ocker and colleagues, in a 2021 paper based on Voyager 1 plasma wave system data, found that the spacecraft was detecting a persistent, low-frequency plasma wave emission that tracked the local electron density in the interstellar medium. More striking, this density appeared to be neither uniform nor gradually varying, but structured, with regions of higher and lower electron density in interstellar space that were consistent with organized plasma filaments extending over hundreds of light years. Nobody put those filaments there. They are a feature of the interstellar medium itself, shaped by the same magnetic fields and turbulence that pervade the galaxy. What this tells us is that the solar system does not sit in a generic, average sample of interstellar space. It sits in a specific structured local environment, the local bubble, a region of hot low-density plasma approximately 0 light-years across that was hollowed out by a series of supernova explosions between 14 and 3 million years ago. The edge of the heliosphere is not merely the boundary of the Sun's influence. It is the meeting place between our solar system's local environment and the ancient, massive legacy of the stars that exploded nearby. Every comet that enters the inner solar system, every interstellar particle that strikes the upper atmosphere of Earth, every particle of cosmic radiation that drives the mutation rate of life, all of it is modulated by conditions at this boundary. The heliopause is not peripheral. It is biologically, chemically, and geologically relevant to every living thing on Earth. And then, just as the Voyager spacecraft were sending back the most scientifically productive data of their careers, 46 years into missions that were designed to last 5, Voyager 1 fell silent. On November 14, 2023, the spacecraft stopped sending readable science and engineering data back to Earth. Mission controllers at the Jet Propulsion Laboratory in Pasadena, California, could still detect the spacecraft's carrier signal, the faint electromagnetic whisper that confirmed Voyager 1 was still alive and still transmitting. But the data being carried by that signal was gibberish. Every measurement, every sensor reading, every system status byte was scrambled beyond recognition, and the team had no immediate idea why. This was not a situation that had a straightforward solution. Voyager 1 was at a distance of approximately 24 billion kilometers when it went silent, a distance so vast that a single round-trip radio message travelling at the speed of light took approximately 45 hours to complete. The spacecraft was running on hardware designed in the late 1960s and early 1970s, before the concept of software updates had been invented in anything resembling its modern form. The engineers and scientists who originally built Voyager 1 were mostly retired or deceased. The documentation for the spacecraft's onboard computers was decades old and incomplete. The team working on the problem was small, underfunded, and operating against the constant background pressure of a program that was technically beyond its original design lifetime by decades. And yet they had to diagnose, from 24 billion kilometers away, which specific component of a 47-year-old spacecraft had failed, and then determine whether that failure could be repaired with a software patch transmitted across the solar system at the speed of light. What followed was one of the most extraordinary feats of remote engineering in the history of space exploration. The story of that recovery is the human heart of this entire chapter of solar system science, and it deserves to be told in full. Suzanne Dodd had been the project manager for the Voyager interstellar mission since 2010. By November 2023, she had shepherded both spacecraft through a succession of crises: fuel system anomalies, instrument failures, the slow, irreversible degradation of radioisotope thermoelectric generators, that had been converting the decay heat of plutonium-238 into electrical power for nearly half a century. Each year, the generators produced slightly less power. Each year, the team had to decide which instruments to turn off to maintain critical functions on the remainder, managing a spacecraft whose power budget was shrinking at the rate of 4 watts per year. When the total power available was already below 300 watts, was an exercise in permanent triage. The November 2023 anomaly was different in kind from the power management challenges the team had navigated for years. It was a communication failure, and it came from a specific identifiable component, the Flight Data System, or FDS. This computer was one of 3 onboard computers that collectively managed Voyager 1's operations. Its job was to collect data from the science instruments and engineering sensors, package that data into a formatted stream of bits, and send it to the communication subsystem for transmission to Earth. What the team discovered, after weeks of painstaking analysis, was that a single chip within the FDS, a chip responsible for storing a section of the flight software, had failed. Not failed completely, in the sense that it had stopped working. Failed partially, in the sense that roughly 3% of the memory stored on that chip had become corrupted and was no longer producing valid data. 3% sounds small. In the context of a spacecraft computer, it is not. The FDS operated on a 69.63 kilobyte total memory, an almost incomprehensibly small amount by modern standards, smaller than the plain text version of a typical academic paper, smaller than many single photographs taken with a modern smartphone. Within that 69.63 kilobytes, every byte had a purpose. The corrupted 3% included code that was interwoven with the data packaging routine. Code that the FDS executed every time it assembled a data packet for transmission. Every transmission was scrambled at the source before it even reached the communication system. The failed chip could not be repaired. There was no mechanism available, no robotic arm, no spare component, no physical access of any kind, to repair a hardware failure on a spacecraft 24 billion kilometers away. The only option was to work around the corrupted memory. That meant physically relocating the code that lived on the damaged chip to other undamaged sections of the FDS memory, rewriting essentially the functional architecture of a 50-year-old computer from across the solar system, testing each patch before sending it, waiting 45 hours for the round-trip confirmation that the patch had arrived and had the desired effect, and then evaluating whether the next step in the repair sequence could be executed. The team who accomplished this was, by any reasonable measure, not large enough for the task. The Voyager mission by 2023 operated on a budget that represented a tiny fraction of what NASA spent on active planetary missions. The people who knew the spacecraft best, the engineers who had been there from the beginning, were gone. What remained was a team that had spent years reverse engineering the original documentation, supplementing it with whatever surviving engineers and scientists could be persuaded to consult, building up a body of institutional knowledge that could only be described as archaeological. They were archaeologists of a live spacecraft, excavating the logic of machines that thought in assembly code, machines that predated personal computers by several years, and they got it working. Between April and September 2024, the team transmitted a series of software patches to Voyager 1, each one carefully computed, checked, and verified against simulation before transmission, that gradually relocated the FDS software from the corrupted chip to intact regions of memory. Each patch had to fit within the surviving memory without disturbing other critical functions. Each required the team to hold their collective breath for 45 hours before they knew whether it had succeeded. And one by one, system by system, Voyager 1 came back. By September 2024, all 5 of the spacecraft's operational science instruments had resumed transmitting valid science data. Voyager 1 was back in interstellar space, measuring plasma waves, particle energies, and magnetic fields in the medium between stars, sending those measurements back to Earth in coherent, interpretable packets for the first time in nearly a year. I want to be direct about how I feel when I think about this story, because the emotion is important. What the Voyager team accomplished in those months represents, to me, one of the most purely human achievements of the space age. Not the most spectacular in terms of visual imagery or public impact. Not the most scientifically transformative in terms of the data it recovered, but in the deeply specific sense of humans sitting in a room, refusing to give up on a machine that was older than most of them, separated from that machine by a distance that light takes 22 hours to cross, methodically diagnosing and fixing a problem that had no precedent in the history of spacecraft engineering. There is something almost mythological about it, something that belongs in the same category as the engineers who guided Apollo 13 home using nothing but arithmetic and a commitment to not losing the crew. The data Voyager 1 recovered, and is still recovering as of this writing in 2025, continues to reshape our understanding of what interstellar space actually is. The plasma wave density measurements that the spacecraft has been making since it crossed the heliopause in 2012 have revealed that the local interstellar medium is not the smooth, homogeneous fluid that pre-Voyager models assumed. It is structured, filamentary, and in some regions unexpectedly dense. In late 2023, shortly before the FDS anomaly silenced the spacecraft, Voyager 1 detected a sudden increase in plasma density. An encounter with what appeared to be a denser filament or cloud embedded in the local interstellar medium. This was not the first such density increase Voyager 1 had recorded, but its timing gave it particular scientific value. It was a reminder, delivered at the very moment when human engineers were struggling to maintain the spacecraft's voice, that the territory being explored was full of surprises. There is also a broader human story in the Voyager missions that goes beyond the November 2023 anomaly and its repair. Both Voyager 1 and Voyager 2 were launched in 1977 carrying golden records, phonograph discs engraved with sounds and images selected to represent the diversity of life and culture on Earth, a greeting from humanity to whatever civilization in the galaxy might someday intercept them. Carl Sagan was a key member of the committee that designed those records. He argued, in the book he wrote with Andruyan about the project, that the records were less a message to alien civilizations than they were a statement about what humanity believed itself to be. A species capable of curiosity, capable of music and mathematics, and the desire to reach beyond its own boundaries. The record contained greetings in 55 languages, sounds of surf and rain and wind, 27 pieces of music spanning from Azerbaijani folk songs to Bach's Brandenburg Concerto No. 2, and 115 images including a nursing mother, DNA's double helix structure, and the Earth as seen from the Moon. Both of those records are now in interstellar space. They will outlast every building currently standing on Earth. They will outlast, in all probability, every institution currently governing human affairs. They will drift through the galaxy for billions of years, carrying their encoded cargo of human achievement, until either they are intercepted by someone who can decode them, or they are vaporized by a collision with interstellar dust, or the galaxy itself evolves into something unrecognizable around them. This is the most extreme delivery in the history of the species. The postage, 47 years of engineering, mathematics, and an endless supply of human stubbornness has been extraordinary, and the mission is not yet over. Both spacecraft are still operating, though each year the margins grow thinner. The power available to Voyager 1 in 2025 is sufficient to operate perhaps 4 science instruments. The team has calculated that the last instrument will likely fall silent sometime in the late 2020s or early 2030s, when the generators can no longer maintain operating temperature for any of the remaining sensors. When that happens, Voyager 1 will continue its journey through interstellar space, silent and ballistic, carrying its golden record into the deep time of the galaxy. But until that moment, it will keep transmitting, it will keep measuring, it will keep telling us things about the territory we are flying through, territory that we are only now beginning to understand, belongs to us as much as any closer address in the solar system. The heliopause is the edge of one definition of the solar system, but there are other definitions, and beyond the heliopause, deeper into the darkness, where even Voyager cannot reach for centuries, the solar system's true boundaries extend to a distance that makes the heliopause look local. The Oort cloud begins roughly 2,000 astronomical units from the Sun. It extends, in the most current estimates, to perhaps 200 Voned astronomical units, nearly a third of the distance to the nearest star. It contains, in theoretical estimates, hundreds of billions of cometary nuclei and an unknown number of larger bodies, all bound to the Sun by gravity too weak to have yet been disturbed by stellar encounters, but real enough to have kept them in orbit for billions of years. We have never directly observed the Oort cloud. We have inferred its existence from the trajectories of long-period comets. Comets like Hale-Bopp, which appears in our skies every 2,520 years, or Hyakutake, which last passed close to the Earth in 1996, and will not return for approximately 70,000 years. These objects arrive from all directions, with random orbital inclinations that have no preferred plane, which means they must be coming from a spherical reservoir rather than the flattened disk that characterises the Kuiper belt. That spherical reservoir is the Oort cloud. Jan Oort, the Dutch astronomer who proposed its existence in 1950, argued from exactly this logic. The distribution of incoming long-period comets requires a vast, roughly spherical shell of icy bodies surrounding the solar system at enormous distances. The Oort cloud was and remains one of the most consequential theoretical constructs in solar system astronomy, a structure that has shaped our understanding of comet dynamics, the solar system's formation history, and the solar system's interaction with the galactic environment, all without a single direct observation to its name 0.21 OF201. With its aphelion of 1,632 astronomical units, lives at the inner edge of this unseen realm, a world whose elongated orbit sends it soaring into the Oort cloud's inner precincts once every 24,256 years before dragging it back toward the Sun. It is a visitor from a region we have never seen, a messenger from the deep time of the solar system, photographed by accident in data collected for a completely different scientific purpose, and recognised for what it is only through the application of algorithms designed years after its first observations were recorded. The question of what else lives in the Oort cloud, and what might have been sent there, is the question that keeps the whole field awake at night. Every discovery in the outer solar system, from the identification of 1992 QB1 to the announcement of 2017 OF201, arrives wearing its scientific significance lightly. The headlines speak of distant icy worlds and mysterious orbits. What they rarely convey, and what I want to spend time conveying now, because I think it is the most important thing about this entire subject, is the scale of what is actually at stake in understanding the outer solar system. Not in the abstract, aspirational sense of expanding human knowledge, though that too. In the specific, concrete sense of understanding where we came from and what the conditions for life in this solar system actually were, and whether those conditions are rare or common in the galaxy. Start with the simplest version of the stakes: impact probability. The Oort cloud, if it exists in anything like the form predicted, contains hundreds of billions of icy bodies. Most of them will remain in their stable orbits for billions of years, undisturbed by stars or the galactic tide. But the galactic tide is not a fixed, constant force. The Sun bobs up and down through the plane of the Milky Way on a period of roughly 64 million years, and as it moves through regions of the galaxy with higher or lower density, the galactic tide on the Oort cloud changes. When the Sun passes closest to the galactic plane, a period known as the galactic plane crossing, the tidal perturbation on the Oort cloud reaches a maximum, potentially sending a shower of comets into the inner solar system over a period of millions of years. The timing of these comet showers has been proposed as a contributing factor to the mass extinction events recorded in the fossil record, including, potentially, the event 66 million years ago that ended the reign of the non-avian dinosaurs. The asteroid that struck the Yucatan Peninsula at that moment is the most famous proximate cause, but the question of what sent that asteroid inward, what disrupted the outer solar system to place it on an Earth-crossing trajectory, remains genuinely open. This is not speculation. There is a statistical correlation in the paleontological record between the timing of mass extinctions and models of the Sun's galactic oscillation. The correlation is debated, the data are imprecise, and the causal chain is complex. But the possibility that the life history of complex organisms on Earth has been shaped at multiple points by perturbations to the outer solar system driven by the galaxy itself, that is not speculation. That is the reasonable conclusion from the available evidence, and it changes the moral weight of understanding the Oort cloud. We are not studying a distant, irrelevant region of space. We are studying the mechanism that has periodically reset the complexity of life on Earth. Now add PlanetNine. If a Neptune or larger planet is present in the outer solar system, at 500 to 1,000 astronomical units, on a highly eccentric orbit, its gravitational influence on the Oort cloud would be enormous. A planet of 10 Earth masses at 700 astronomical units exerts a tidal force on the inner Oort cloud that would periodically scatter objects into the inner solar system. The existence of PlanetNine, if confirmed, would need to be incorporated into models of long-period comet delivery, models of the flux of impactors in the inner solar system, and ultimately models of the extinction risk to Earth over geological timescales. This is not a remote concern for future generations. These are calculations that matter for understanding why the biosphere of Earth looks the way it does today. The stakes escalate further when we consider the solar system's formation history. The current distribution of objects in the outer solar system, the Kuiper belt, the scattered disk, the sednoid population, and the inferred Oort cloud, is a frozen record of the dynamical history of the solar system during its first billion years. In that first billion years, the giant planets were migrating through a more densely populated protoplanetary disk, scattering smaller bodies in all directions, sculpting the architecture of the outer solar system in ways that models are still struggling to reproduce accurately. The NICE model, first proposed in 2005 and named after the French city where its authors worked, describes a period of giant planet instability in which Jupiter, Saturn, Uranus, and Neptune underwent a period of orbital rearrangement triggered by resonance crossing, scattering vast numbers of Kuiper belt objects and potentially sending a late bombardment of material into the inner solar system. This late heavy bombardment, as it is called, may have delivered significant quantities of water and organic material to the early Earth, potentially playing a role in the origin of life. The NICE model makes specific predictions about the distribution of objects in the outer solar system that can be tested against observation. The sednoid population, Sedna, 2012 VP113, 2017 OF201, and whatever else is discovered in their orbital family, is a critical test. These bodies live in orbits that current models of Neptune-driven scattering struggle to produce in the quantities observed. Their high perihelia, their wide semi-major axes, their distribution in physical space, all of these constrain the history of the giant planet's migration in ways that have not yet been fully incorporated into any single model. Each new sednoid discovered either fits the models better or requires the models to be revised. 2017 OF201, with its outlier perihelion longitude that does not fit the PlanetNine hypothesis, may simply be evidence that the outer solar system is messier and more dynamically complex than any single model can currently capture, a reservoir of mixed dynamical origins that requires multiple mechanisms to explain. There is a phrase that planetary scientists use when they confront this complexity, and I think it is worth quoting directly. The outer solar system is not a museum. It is not a static collection of primordial debris sitting exactly where the formation of the solar system placed it. It is a living, dynamic system, living on timescales of millions to billions of years rather than human lifetimes. but dynamic in the sense that objects are constantly being moved, scattered, sent inward or outward by gravitational interactions that have been operating continuously for 4.6 billion years. What we observe today is not the original configuration. It is the latest snapshot of a process that is still unfolding. This matters enormously for comparative planetology, the study of other planetary systems by comparison to our own. The Kepler Space Telescope, the TESS mission, and ground-based radial velocity surveys have now identified thousands of exoplanet systems. Many of these systems look nothing like ours. They have super-Earths, planets with masses between 2 and 10 Earth masses, sitting in orbits far inside the distance that Mercury occupies in our solar system. Our solar system has no super-Earth. It has a gap between Mars and Jupiter that most planetary theorists now believe was created by Jupiter's early migration. The Grand Tack, as it is called, which swept through the inner solar system like a giant broom and reduced the amount of material available to build rocky planets. Did the Grand Tack also scatter a super-Earth outward, a body of several Earth masses that was flung into the outer solar system and now sits in a wide, eccentric orbit at hundreds of astronomical units from the Sun? If PlanetNine is confirmed, and if its mass turns out to be in the 5 to 10 Earth mass range that most models predict, then yes, our solar system had a super-Earth all along. It was just hiding in the darkness, 600 times further from the Sun than Earth, invisible to every instrument we possessed until the last decade of searching brought it into range. The implications of that for our understanding of solar system formation are staggering. It would mean that the dynamical events of the early solar system were far more violent than the standard models suggest. That entire planetary bodies were ejected from the inner solar system and parked in remote orbits by gravitational encounters that left no obvious trace in the architecture of the planets we can see. And it would mean that what we see when we look at other planetary systems, those densely packed inner system configurations with their close-in super-Earths, may all be concealing outer system bodies that we cannot yet detect with available instrumentation. The argument runs in the other direction too. Many of those exoplanet systems contain super-Earths. If planet formation systematically produces super-Earths, and if our solar system's lack of an obvious inner super-Earth is explained by dynamical ejection to the outer system, then having a super-Earth in the outer system is the normal state of affairs, not the exception. We may not be unusual. We may simply have hidden our super-Earth where nobody could find it for 4 billion years, and we are only now, in the second decade of the 21st century, closing in on its location. The Vera-Rubin Observatory, the WISE and NEOWISE mission data, the IRIS-Akari infrared candidate, all of these represent converging lines of evidence and methodology pointing toward the same dimly lit region of the outer solar system. The candidate identified by Fan and colleagues in April 2025 may or may not be PlanetNine. The follow-up observations with DECAM may confirm it or eliminate it, but the method is sound, the search is active, and the instruments are improving. Rubin will survey the sky every few nights for 10 years, to a depth that no previous ground-based survey has achieved, and its data will be processed in real time for moving objects by algorithms trained specifically for the purpose. If PlanetNine is there, if it falls within Rubin's detection limits at its current position in its orbit, the probability is high that Rubin will find it within the first 3 years of full operation. And if Rubin does not find it, then we have ruled out the simplest versions of the hypothesis across a large region of sky, and the question of what is causing the orbital clustering of extreme trans-Neptunian objects will sharpen rather than disappear. The alternative explanations, a population of smaller, undetected bodies rather than a single large planet, or a primordial black hole in a wide orbit rather than a conventional planet, or a combination of galactic tide effects and stellar encounter history, will move from the margins of the discussion to the centre. No version of the outcome eliminates the fundamental mystery. The clustering signal, whatever its ultimate explanation, is telling us something real about the structure of the outer solar system. that something remains, as of this writing, one of the most consequential unanswered questions in modern planetary science. But before we can fully grasp what any of this means, we need to ask the deepest question of all. Not where PlanetNine might be, not how 2017 OF201 got its peculiar orbit, but what the discovery of hidden structure at the edge of our solar system means for our understanding of the solar system as a place capable of sustaining life. And for that, we need to go back to the beginning, not just of the solar system, but of the discipline of looking for things we couldn't see. The history of solar system science is largely a history of finding things in places the prevailing model said they could not be. It is a history of confident assertions, followed by embarrassing retractions, followed by new confident assertions that are, in turn, overturned. This is not a failure mode of the discipline, it is the discipline working correctly. But understanding its pattern is essential to placing the current discoveries in their proper context. When Pluto was discovered in February 1930 by Clyde Tombaugh at the Lowell Observatory in Flagstaff, Arizona, it was heralded as the fulfillment of a prediction. Percival Lowell, the eccentric Boston astronomer who had spent years arguing, incorrectly as it turned out, that the canals of Mars were the irrigation works of a dying civilization, had also spent enormous energy and money searching for a planet X beyond Neptune. His prediction was based on observed perturbations in the orbits of Uranus and Neptune that he believed required an undiscovered planet to explain. Tombaugh found Pluto by running the same kind of blink comparator survey that Jewett and Liu would use decades later, systematically comparing photographic plates taken days apart to find moving objects. He found Pluto almost exactly where Lowell had predicted Planet X would be. It seemed like a triumph of mathematical astronomy. It was not. Pluto turned out to be far too small to produce the gravitational perturbations that had motivated the search. When Voyager 2 flew past Neptune in 1989 and gave us precise measurements of its mass, astronomers recomputed the Uranus orbit and found that the perturbations that Lowell had been trying to explain were an artifact of imprecise observations, not a signal of a real undiscovered planet. Pluto was found not because Lowell's prediction was correct, but because Tombaugh was extremely thorough and extremely persistent. He examined over 90 million star images before finding the slow-moving dot that turned out to be Pluto, and because Pluto happened to be in the region of sky where the survey was operating. This history is relevant to the current search for PlanetNine in a specific and important way. The orbital clustering of extreme trans-Neptunian objects may not be pointing unambiguously at a real object, in the same way that Lowell's orbital perturbations of Neptune did not point unambiguously at Pluto. The clustering signal might be real, caused by a genuine undiscovered planet. It might be a statistical artifact of incomplete sky coverage and observational bias. It might be partially real, caused by a combination of dynamical effects, none of which alone is sufficient to explain the full signal. The history of planetary prediction from orbital anomalies includes Leverrier's brilliant prediction of Neptune in 1846, which was triumphantly confirmed, and Lowell's prediction of Planet X, which was not. We do not, in advance of the discovery or non-discovery, know which category the current case falls into. What we do know is this: the analysis has gotten more sophisticated with each iteration. The 2024 Batygin and collaborators paper is a far more rigorous treatment of the observational bias problem than any previous analysis. The dataset has grown substantially since 2016, with dozens of new extreme trans-Neptunian objects added to the sample. The statistical tools applied to the data have improved, and the result, a 5 sigma preference for the PlanetNine inclusive model over the PlanetNine free model, is meaningful if not definitive. It means that the data, as best as they can be corrected for known biases, prefer the existence of PlanetNine. Whether they truly require it is a harder question, and the honest answer is that the scientific community remains genuinely divided. The discovery of 2017 OF201 and its outlier longitude of perihelion introduces a new constraint. As Sihao Cheng and his collaborators note in their paper, there are essentially two responses to the fact that 2017 OF201 does not fit the predicted clustering. The first is to conclude that the clustering signal is less clean than the hypothesis requires, and that the probability of the clustering occurring by chance is higher than the 2016 estimate of 0.007% implied. The second is to conclude that PlanetNine, if it exists, must have orbital properties different from the simplest estimates. Properties that allow for a mixed population of both clustered and unclustered objects at the relevant orbital distances. Both are legitimate scientific responses. Both have been explored in the literature. Neither provides a clean resolution to the question, what Cheng et al. Also note, however, is that the discovery of 2017 OF201 provides striking, independent evidence that the outer solar system is more densely populated than surveys have so far revealed. The existence of this single large object with an extreme orbit, discovered serendipitously in archival data not designed for solar system science, implies the existence of a substantial unseen population of similar bodies. Population estimates based on survey completeness suggest that for every large trans-Neptunian object with an extreme orbit that has been found, there are dozens or hundreds more waiting to be discovered. Some of those undiscovered objects may show orbital clustering, some may not. The complete distribution, which will only become available once surveys like the Vera Rubin Observatory's LSST have operated for several years and discovered the currently invisible population, may look quite different from the handful of objects available in 2016 and quite different again from the handful available in 2025. This is the incompleteness problem, and it is, in some ways, the most fundamental uncertainty underlying all current discussions of the outer solar system. We are making strong inferences from a very small and potentially biased sample. With Rubin, the sample will grow by roughly a factor of 10. The orbits currently known, the handful of extreme objects that have motivated the PlanetNine hypothesis, the sednoids, the scattered disk objects, will be supplemented by hundreds of new discoveries that will either clarify or scramble the pattern. The next decade will either confirm that the clustering is a robust feature of the outer solar system requiring a planetary explanation, or reveal that it was an artifact of our limited sample size, dissolving as the population expands. I should also address a topic that tends to lurk at the edges of public discussions of PlanetNine without always being explicitly stated: the possibility that what Batygin and Brown found is not a planet at all, but a primordial black hole. This hypothesis, proposed by Jakob Scholz and James Unwin in 2019, observes that a black hole of 5 to 15 Earth masses, a so-called primordial black hole formed in the extreme conditions of the early universe, would have the same gravitational influence on distant Kuiper Belt objects as a conventional planet of the same mass. A black hole in this mass range would be extraordinarily small. Its event horizon would be roughly the size of a grapefruit, and effectively invisible to optical surveys. It would not reflect sunlight. It would not emit infrared thermal radiation in quantities detectable by current instruments. The only way to find it would be through its gravitational effects on other bodies, or through the detection of gamma-ray emission from the Hawking evaporation and the slow accretion of interstellar material, neither of which would be easy with current facilities. The primordial black hole hypothesis was explicitly considered by Fan and collaborators in their 2025 infrared paper because its implications for their search strategy are important. If the outer solar system object responsible for the orbital clustering is a primordial black hole rather than a conventional planet, it would not be detectable in the IRAS and Akari far-infrared surveys that they used. A black hole would not radiate thermally in the way a planet does. The detection of a far-infrared candidate in those surveys would, if confirmed, effectively rule out the black hole hypothesis, which is one reason the Fan et al. Candidate is scientifically interesting even beyond the immediate question of whether it is PlanetNine. The Schultz-Unwin hypothesis was greeted with the mixture of interest and skepticism that creative but speculative ideas typically receive. Primordial black holes in this mass range are not ruled out by current observations, but their existence would require specific conditions in the early universe that are not independently confirmed. The hypothesis is consistent with the orbital clustering data in exactly the same way that the conventional planet hypothesis is consistent, which means the orbital clustering data alone cannot distinguish between them. A black hole at 600 astronomical units is dynamically equivalent to a planet at 600 astronomical units, from the perspective of its gravitational effects on small bodies nearby. Distinguishing between the two requires either a detection of thermal emission, possible only if the object is a planet, or a gravitational microlensing event, possible if the object is a black hole, but also possible if it is a planet, or the direct confirmation of a positional detection consistent with the object's predicted motion. All of these discussions, the observational bias debate, the incompleteness problem, the primordial black hole hypothesis, the dynamical implications of 2017 OF201 lead to the same fundamental conclusion. We are not at the end of this story. We are at the beginning of the chapter in which the decisive evidence arrives. The tools are in place, the data will come, and when it does, the answer will almost certainly be stranger and more complex than any of the current hypotheses individually predict. The outer solar system has been surprising us for 35 years. There is no obvious reason why it would stop now. The deeper truth, and this is the one I find myself returning to in the middle of the night, is that the outer solar system is not primarily an astronomical subject. It is a geological and biological subject. It is part of the story of why the Earth looks the way it does, why life exists here, why the conditions for complex organisms were maintained for long enough for intelligence to emerge. The comets that delivered water and organics to the early Earth came from the outer solar system. The bombardment events that periodically reset the evolutionary clock came from the outer solar system. The galactic perturbations that destabilize the Oort cloud and send long-period comets screaming inward toward the Sun come, in the final analysis, from the structure of the galaxy itself. But they are mediated by the architecture of the outer solar system, including whatever large bodies may be living there in the dark. Understanding the outer solar system is not, ultimately, about finding a ninth planet. It is about understanding the complete gravitational environment in which life on Earth has evolved, an environment that extends from the Sun's core to the boundary of the Oort cloud, nearly a light year away. We have understood the inner parts of that environment reasonably well for over a century. We are only now beginning to understand the outer parts, and what we are finding is that the outer parts are not a negligible addendum to the interesting inner regions. They are a dynamic, consequential, deeply strange territory that has been shaping the story of life on Earth since the beginning. The next decade in outer solar system science is going to be unlike any that preceded it. Not because the questions are new, they are, in most cases, the same questions that have been driving the field for 30 years, but because the instruments are finally catching up to the questions, and the gap between what we want to know and what we can measure is narrowing at a rate that was unimaginable as recently as 2010. The Vera Rubin Observatory, operated by a consortium of US and Chilean institutions on a mountaintop in the Chilean Atacama Desert, began its formal legacy survey of space and time in early 2026. This is the telescope that the planetary science community has been waiting for, with a mixture of anticipation and barely suppressed anxiety. Its 8.4-metre primary mirror collects light from a field of view 3, 5 degrees in diameter, roughly the width of 7 full moons laid side by side, and its 3.2 gigapixel camera, the largest digital camera ever built for astronomical use, records that field in a single exposure to a depth that would detect a candle flame at a distance of 400 kilometers. Every night it operates, Rubin will image tens of thousands of square degrees of sky, reaching limiting magnitudes deep enough to detect trans-Neptunian objects smaller than 100 kilometers in diameter, at distances beyond 50 astronomical units. For the search for PlanetNine specifically, Rubin's survey is expected to discover roughly 10 times as many trans-Neptunian objects as are currently known. The current total of known trans-Neptunian objects stands at approximately 5,000. By the end of Rubin's 10-year survey, that number will be close to 50,000, perhaps more. Within that enlarged population, the statistical debate about whether the orbital clustering of extreme objects is real or artifactual will be decisively resolved. If the clustering persists in a sample 10 times larger, corrected for the extremely well-characterized survey geometry of Rubin's systematic sky coverage, then it is real, and the statistical case for PlanetNine will be essentially unassailable. If the clustering dissolves into a more uniform distribution as the sample size grows, then it was a small number statistical artifact, and the field will need to redirect its energy toward alternative explanations. Rubin will also directly detect PlanetNine if it currently sits in the right region of sky and the right phase of its orbit. The telescope is sensitive enough to detect a Neptune-sized planet at up to several hundred astronomical units in a single night's exposure. At perihelion, where PlanetNine, at its predicted distance of perhaps 400 to 800 astronomical units, is closest to the Sun and therefore brightest, Rubin should be able to find it within the first few years of survey operation, assuming the predicted sky position is roughly correct. If PlanetNine is currently near aphelion, at distances of 1,000 astronomical units or more, it may be too faint for Rubin's optical sensitivity, and the search will extend into the infrared domain that future space telescopes are designed to access. The Iras-Akari candidate identified by Fan and collaborators in 2025 will be fully characterized, confirmed or eliminated within the first year or two of Rubin's operation. If the candidate is real, Rubin will find it. Its predicted position, computed from the two archival far-infrared detections separated by 23 years, constrains the object's sky location to a specific region that Rubin will survey repeatedly over the course of its observing program. A moving object at 500 to 700 astronomical units would show measurable displacement on the sky over a period of months. Slow, but detectable by Rubin's automated moving object detection pipeline. If the candidate is spurious, an artifact of the difficulty of working with decades-old infrared survey data, Rubin will find nothing at the predicted position, and the search will continue. The question of what happens beyond Rubin, beyond the reach of any ground-based optical telescope, in the true depths of the outer solar system, is one that the heliophysics and planetary science communities are actively addressing. The most ambitious proposal currently under consideration is the Interstellar Probe concept, a NASA-studied mission that would send a spacecraft on a trajectory optimized for the study of the heliospheric boundary and beyond, reaching approximately 1,000 astronomical units within 50 years of launch. This is a mission that would, for the first time, sample the dust, plasma, and neutral gas of the true interstellar medium at a wide range of distances from the Sun, providing direct measurements that Voyager, admirable as it is, can only partially supply from its single trajectory through a single region of the heliopause. The Interstellar Probe concept also offers, intriguingly, a possibility for direct encounter with, or at least close observation of, Oort cloud objects during its transit of the inner Oort cloud region at distances between 100 and 0 astronomical units, a region that no spacecraft has ever purposefully entered. Whether any budgetary or political momentum will translate this concept into an actual flight mission remains deeply uncertain as of early 2026. But the scientific case for such a mission has been made with remarkable thoroughness in the recent decadal survey for solar and space physics, and the conversation in the community is shifting from whether such a mission is desirable to whether it is fundable. Meanwhile, the James Webb Space Telescope, the largest and most powerful space telescope ever deployed, which began science operations in 2022, is capable of contributing to the outer solar system story in ways that its designers did not specifically target. Webb's near-infrared and mid-infrared instruments can characterize the surface composition of trans-Neptunian objects in ways that ground-based telescopes cannot, and this compositional information provides constraints on the formation history and thermal evolution of these bodies. Webb has already returned detailed spectroscopy of several Kuiper Belt objects, including information about the presence of water ice, carbon dioxide, methanol, and complex organic molecules on their surfaces. Molecules that tell us something about the chemistry of the young solar system and about the potential for organic material to be delivered to the inner solar system by cometary impacts. The compositional analysis of 2017 OF201, if and when Webb or a future telescope obtains a spectrum of sufficient quality, could be particularly informative. The object's colour index from the Discovery paper places it among the reddest trans-Neptunian objects, consistent with a surface rich in complex organic molecules, what astronomers call tholins, that form when methane and nitrogen ices are irradiated by cosmic rays over long timescales. The redness of Sedna, the redness of 2017 OF201, and the redness of other extreme trans-Neptunian objects suggest a population of objects that have spent billions of years in the outer solar system, far from the sun's warming radiation. A cosmic ray processing of surface ices has been building up a dark, red organic crust. This is the preserved biochemical raw material of the early solar system, not life itself, but the precursor molecules from which, under different circumstances, life's chemistry might have emerged. There is a line of thinking in astrobiology that regards the outer solar system as the solar system's freezer, a vast repository of organic molecules, water ice, and volatile compounds that were produced in the protoplanetary disk and then scattered outward by planetary migration, preserved for billions of years at temperatures approaching absolute zero and periodically delivered to the inner solar system by gravitational perturbations. This delivery mechanism, cometary impacts carrying organic material and water to the surfaces of the inner planets, may have been one of the key processes enabling the emergence of life on Earth. The outer solar system is not merely the backdrop to the story of life. It may be one of the story's indispensable supply chains as the 2020s progress, the convergence of ground-based surveys like Rubin, space-based infrared capabilities like WISE and its successors, the continuing slow journey of both Voyager spacecraft deeper into interstellar space, and the growing sophistication of computational models for outer solar system dynamics is producing a rate of discovery and insight that would have seemed wildly optimistic to the astronomers who found 1992 QB1 in the early days of CCD astronomy. We have moved in 30 years from a solar system that ended neatly at Pluto's orbit to a solar system whose outer boundaries extend to distances we cannot yet observe directly, populated by bodies whose orbits suggest the gravitational influence of one or more large, hidden objects, and bounded by a heliopause whose detailed structure reveals the nature of our local interstellar environment in ways that have direct implications for the history of life on Earth. Every instrument that points toward the outer solar system in the next decade will find something unexpected. That is not a prediction, it is a pattern. The outer solar system has been surprising us with every improvement in our ability to observe it, without exception, since the first trans-Neptunian object was discovered in 1992. There is no reason to expect this pattern to end. There is every reason to expect it to accelerate. The question is not whether there is something out there. There manifestly is. The questions are what it is, how much of it there is, and what it means for the story of how this solar system, this particular configuration of matter, orbiting this particular star in this particular galaxy, produced the conditions that made us possible. Those questions are not answered. They are right now barely properly formed, and the instruments we are deploying to answer them will produce, in the next decade, a transformation of our understanding of the solar system's outer reaches that will rival and possibly exceed anything that has come before. There is something that strikes me every time I spend time with this material about the relationship between human timescales and solar system timescales. We have been doing science, systematic, empirical, tool-assisted science, for perhaps 500 years in its modern form. The outer solar system has been doing whatever it does for 4.6 billion years. The imbalance is, in a word, vertiginous. We are newcomers trying to read the handwriting of a process that finished writing before the first cell divided on Earth. And yet here we are, reading it. Not completely, not without error, not without enormous amounts still hidden from us, but reading it. We found Sedna, a frozen world the colour of dried blood in an orbit so extreme it had no right to exist. We held up its orbit like a message from the deep past and said, something is responsible for this. We found 2017 OF201 hiding in the archival photographs of a cosmological survey, and we measured its 256-year circuit around the Sun with enough precision to say, its orbit does not cluster with the others, and that means something. We repaired a 50-year-old spacecraft from 24 billion kilometres away, working in 45-hour increments, and got it to tell us about the plasma wall at the edge of the Sun's domain, and about the filamentary structure of interstellar space beyond it. Each of those things required someone to sit in the dark for a long time, with data that didn't quite make sense, and refuse to accept the easy explanation. That refusal, that particular flavour of scientific stubbornness, is, I think, the most underappreciated feature of the whole enterprise. It is not glamorous, it is not the stuff of dramatic press releases, but it is what happens between the dramatic press releases, and it is where the actual science lives. What lurks at the edge of our solar system is not simply a planet, or a plasma wall, or a population of frozen worlds in 24,000-year orbits. It is something harder to name than any of those things. It is the accumulated evidence that our address in space is larger and stranger and more consequential than we knew. That the darkness beyond Neptune is not a void but a populated, dynamic territory that has been silently shaping the conditions for life on Earth for billions of years. That every comet that has ever crossed the sky over this planet, every blazing visitor that frightened the ancients and electrified the astronomers, was a messenger from out there, sent inward by forces we are still in the process of identifying. The edge of our solar system is not where things end. It is where the oldest questions begin. What is out there? We don't know yet. Not fully, not in a way that settles anything. But we are closer than we have ever been, with better instruments than we have ever had, asking sharper questions than we have ever formulated. And the darkness, for the first time, is beginning to answer. The next discovery is already in the data somewhere, waiting for someone to look.